welcome to week 14 of our semester and our last two video PowerPoint lectures. We begin with chapter 15, and chapter 15 covers lipids. So let's begin. Lipids, what are they? They are biological molecules that are insoluble in water, but they are soluble in nonpolar solvents. So insoluble in water. That's telling us something about their structure. It's giving us a heads up. Okay, so if they're insoluble in water, they're going to have a nonpolar part to them. Okay, and they are soluble in nonpolar solvents. So again, it is giving us a heads up about their structure. So let's continue with lipids. Lipids, they have a wider spectrum of compositions and structures. And that is because of the way they're defined. All right, so lipids, the way we just defined them, it's based on their physical properties and specifically based upon their water solubility. So lipids, they are waxy, greasy, or oily compounds that are found in both plants and animals. Wax coating, right? The wax coating that protects plants. Lipids. Lipids are used as energy storage. They are also the structural components of the cell membranes, as we'll see later. And they serve as insulation against the cold. So let's continue on, keeping in mind that really broad definition, okay? Insoluble in water and soluble in organic solvents. So that could be a lot of compounds. So how do we classify lipids then? Okay, lipids are in turn divided into saponifiable lipids. What does that mean? Well, you might remember from our study of esters, right? Esters were saponifiable. They underwent saponification. So a saponifiable lipid is going to contain an ester or esters that can undergo saponification. Again, recall back in our earlier chapter on esters, what's saponification? It's simply a base hydrolysis, okay? So saponifiable lipids are going to contain esters which undergo base hydrolysis, saponification. Who are they? Well, they are the waxes, the triglycerides, the phosphoglycerides, and the sphingolipids. And then we have the non-saponifiable lipids. Just as the name says, they are not going to have an ester group and they cannot be saponified. Who are these? Well, they're the steroids and they are the prostaglandins. All right, let's focus first on our saponifiable lipids. Saponifiable lipids are then broken down again. They can be divided into different groups. We have the simple lipids. Simple lipids contain two types of components. A fatty acid and an alcohol. And then we have complex lipids. Lipids contain more than two components. They might contain fatty acids and alcohol as well as some other components. So let's put everything in perspective that we have just seen. So we defined what lipids are, very broad definition. And then we said we can take that very broad category and we split it into saponifiable lipids and non-saponifiable liquids. Who are the non? They're the steroids, the prostaglandins. The saponifiable, simple, complex. We're going to start over on this side, okay, of our classification scheme with the saponifiable lipids. And we begin by talking about fatty acids. Fatty acids, what are they? Well, they are long-chain carboxylic acids. Recall, right, earlier chapter, carboxylic acids. When you hear that name, this structure should come to mind. This is the general structure of a carboxylic acid. A carboxylic acid contains the carboxyl group. Carbon, doubly bonded to an oxygen, so that's a carbonyl. The carbonyl that's bonded to a hydroxyl group. That is a carboxyl group. Remember also, okay, that you may see the condensed structures for carboxylic acid. So you should be able to identify a carboxylic acid either through the expanded right here and or any of these condensed ways of writing a carboxyl group. All right, so a long chain carboxylic acid. Here we go. Okay, that just means that this R group, that chain of carbons, is long. Okay, so here would be an example of a fatty acid. Fatty acids have two parts to them. You see a polar hydrophilic head and a non-polar hydrophobic tail. Remember, every single functional group that we talked about, we went through physical properties, okay? How their structure affected physical properties. And here we are applying it, okay? Remember that carboxylic acids we said were polar, right? So they were water soluble. That part is water soluble. But then we have this large hydrocarbon part, which is nonpolar, and we call it hydrophobic. It's not going to be water soluble, it'll be water insoluble. Hydrophilic means loving water. Hydrophobic means hating. So oftentimes what chemists do, rather than writing the full chain out, you may see a fatty acid designated as such. So that's here coming out of it. All right, that's the nonpolar tail. And then they'll just show the carboxyl group, the polar head. Okay, so properties of fatty acids. So that long, right, non-polar carbon chain, all right, the tail, as it's called, of the fatty acid. It's the biggest part of the fatty acids, so it is going to be responsible for most of the fatty or oily characteristics of lipids. The carboxyl group, on the other hand, is a tiny part, okay? It is, yes, it is hydrophilic. It loves water, all right? The carboxylic acid, right, is water soluble. So that part of a fatty acid under basic conditions, okay, which would be physiological pH 7.4, that carboxyl group is going to be water soluble. All right, so there again, there we see that carboxylic acid group. Okay, so remember when we studied carboxylic acids, we said they're acidic, right? So when we place them in water, okay, physiological pH, all right, water, just slightly basic, okay, what's going to happen? Well, just exactly what we saw with our carboxylic acid functional group discussion. That acidic proton, right, is going to be given up. Carboxylic acids are proton donors. So it's given up to the water and we form carboxylate ions. All right. Remember, the carboxylate ion is water soluble, really water soluble. okay, because of the fact that you have that charge, okay? All right, so as a result, let's see what happens. Fatty acid micelles, our next topic. In aqueous solutions, fatty acids are going to associate with each other in spherical clusters that we call micelles. In the spherical cluster called a micelle, what happens is that hydrocarbon tails, those long hydrocarbon tails, are going to all be pointing one direction. They're going to tangle each other up. All right. How? Dispersion forces. That's all they have going for them. And if they're all tangled up, then that's going to leave the carboxylic acid part, all right, the pointing in another direction. So it's going to leave a shell of polar carboxylate ions facing outwards. And that is what will be in contact with the water and water soluble. So this is what we're talking about in aqueous solution. Fatty acids are going to associate with one another in this manner, okay? You're going to see attractions of the long hydrocarbon tails with each other, just with the dispersion forces, forcing the carboxylate portion to point outwards, giving you a shell, right, of charged species, pointing towards the water. Imagine water all out here, which is going to hydrogen bond. Okay. Micelles, they are important in the transport of insoluble lipids in the blood. Also, we're going to see later on that these micelles are important in the actions of soaps. All right, continuing with our fatty acids characteristics. So what we see with fatty acids is that they are usually straight chains of carbons, no branching, okay? And they're about 10 to 20 atoms in length. They usually have an even number of carbon atoms, and that includes counting the carboxyl carbon. The carbon chains themselves, when we look at them, they might be saturated. Remember what saturated means? All single bonds, every single carbon has its maximum number of hydrogen atoms attached. Or they could even be unsaturated. Unsaturated means that they contain double bonds. So we've got a couple names we're going to throw out at you here, right? If your fatty acid has just one double bond, it's referred to as a mono unsaturated fatty acid. Contains just one double bond, all right? If it has more than one double bond, we call it a polyunsaturated fatty acid. Continuing with our characteristics. So other than the carboxyl group and double bonds, there are usually no other functional groups found in a fatty acid. So remember, we can have a size range between 10 and 20 carbons, all right? The shorter fatty acids have lower melting points than the longer ones, all right? For instance, stearic acid, okay, 18 carbon long, and that includes the carbonyl carbon, right? And its melting point, I believe, yes, melting point is 70 degrees Celsius. Palmitic acid, 16, right, carbons long, 63. So the shorter fatty acids, less carbons, right, okay, less dispersion force interaction, all right, easier to melt, all right, easier to break apart, not as much energy required. Double bonds, whoops, we misspelled here. This should be cis, okay? can be cis, C-I-S, cis or trans, okay? But they are usually in the cis configurations. All right, remember what cis meant in relation to a double bond. All right, so in that big long carbon chain, right, of a fatty acid, we might see a double bond, right? And that means that the rest of the carbon chain, right, what's around it, same side of that double bond. Okay, so typically they can be cis or trans, but most usually they are in the cis configurations. Okay, all right, more on these saturated and unsaturated fatty acids. All right, so the cis double bonds that we see most often in unsaturated fatty acids, what that does is it puts an inflexible kink, so to speak, in the carbon chain. And that inflexible kink prevents a molecule of an unsaturated fatty acid from packing together in a nice, tight way, all right? Saturated fatty acids pack tightly together, for instance, okay? Let's look at an example. So the saturated fatty acids, no double bonds, okay? They fit closely together in a regular pattern because of their geometry. And what happens here is that results in a higher melting point. If they're packing closer together, you're going to have stronger dispersion forces, all right, a lot more of them. And in order to melt, we have to overcome those dispersion forces. So we have to put in more energy. This is what we're talking about. So here we have 3 molecules. We're showing how in a saturated fatty acid, because of the structure, remember 109.5 degree bond angle. So this is one of those structures where there's a carbon at every one of these junctures. We talked about this type of a structure, okay? And then there's the requisite number of hydrogens, okay? So that's what we see in our saturated fatty acids. So let's imagine an unsaturated fatty acid. And again, most of them are cis, all right? So cis double bonds put a kink in the structure. So let's look at what we're talking about here. So here we see the carboxylic acid end, okay? And a long chain of carbons. And then, oh, this is a mono unsaturated, all right? Because it's just one double bond and it is cis. And notice how it puts a kink in the structure. All right, so if we take a number of this type of molecule, they're not going to fit together nice and tightly in a regular pattern because of the presence of this cis double bond. All right, trans double bonds, which don't occur as often, all right, it turns out, do not have the kink. All right, so although they don't have the kink, most often in the fatty acids we find the cis. Okay. Let's look at a real life example. Okay, stearic acid. Stearic acid is a saturated, okay, fatty acid. We're going to look at oleic acid. Oleic acid is a mono unsaturated, okay, one double bond. And linoleic acid has 2 double bonds. Okay, so it's a polyunsaturated. All of them have the same number of carbons, all right? But yet, despite the fact that they have the same number of carbons, these differences in the structure affect their melting points drastically. All right, so let's look at stearic acid. 18 carbons. Okay, again, look, they're all single bonds. Okay, carbon-carbon single bonds. Again, remember there's a carbon here. All right, again, we went through this type of structure. We don't use it that often, but you do see it in books. So every single one of these has a carbon. You can go through it and how many hydrogens it requires to give you 4 double bonds. So 2, right? 2, 2, 2, and this last one over here has 3. All right, so it's saturated. And what did we say about saturated fatty acids? Okay, they pack nicely together, okay, because of their arrangement. Okay, so you're going to have a number of them packed nicely together, close, and we're going to have to break all of those forces, dispersion forces, before it melts. Okay, and let's look at oleic acid. Again, 18 carbons, one double bond at cis. Okay, notice how the ring is coming out, same side, right? Or not the ring, but the two ends, right? Same side. It's monounsaturated. Not going to fit together as nicely as we saw because of that kink, okay? That keeps the fatty acid from fitting nicely and closely together. And then here's a di, right? A poly, all right, unsaturated fatty acid. Two double bonds, kinked, okay, keeping them from forming that nice, organized, packed structure, okay? So melting point wise, the one that takes the most energy, right, to break, right, to melt, to change states, highest melting point, 71 degrees, okay? One double bond, not going to be, okay, not going to be 71, it's 13, quite a difference, okay? And with the two, we expect it to be even less than the 13 degrees Celsius. There it is, -5, okay? Alrighty. All right, so still on fatty acids, let's talk about something called essential fatty acids. Most of the fatty acids that we need, all right, for our body functions can be synthesized in the body. However, two fatty acids, linoleic and linolenic acid, they're both polyunsaturated fatty acids with 18 carbon atoms. They cannot be synthesized in the body, and instead we have to obtain them from our diet. So here's one of them, okay, and here's the other, right? So they're both polyunsaturated, and we cannot synthesize them in our bodies, so we have to get them from our diet. These are what we call essential fatty acids. Where do we get them from? Both of these are found in plant and fish oils. So that's why it's really important that you don't limit your diet to certain things, and exclude certain things. Particularly vegans. Vegans have a lot of issues with some of these things, getting the appropriate fatty acids, and as we see down the line, amino acids. Okay, in the body, these essential fatty acids are used to produce hormone-like substances that help to regulate your blood pressure, blood clotting, blood lipid levels, your immune response, and inflammatory reactions. Okay, moving on to the structure of fats and oils. All right, now we have a background in our in fatty acids. We can move on to fats and oils, and we begin our discussion of fats and oils talking about triglycerides. Animal fats and vegetable oils. They are esters that are composed of 3 molecules of a fatty acid connected to a triol known as glycerol. Okay, so I'm using some of the terminology that we learned when we talked about alcohols, right? Okay, triol, 3 alcohol units in it. So when 3 molecules of a fatty acid connect to, right, and form an ester with a glycerol molecule, this gives you what is called a triglyceride or a triacylglycerol. Let's look at the actual structure of glycerol. You might remember it from our discussion of alcohols, right? We talked about triols, and glycerol was an example. This is, of course, is a common name, right? Okay. And so we take glycerol, a triol, and alcohol, and we combine it with 3 molecules of stearic acid. Stearic acid, look at that big long carbon chain, 18 carbons. All right, it is a fatty acid. So when you combine 3 units of fatty acid with glycerol, we get a reaction that occurs that we saw back in our chapter on acid derivatives, right? This produces an ester. There we go. We've gone from a carboxylic acid and an alcohol to an ester. Okay, 3 of them, right? Every place where we had the alcohol, right? Okay, we combined and it gave us an ester. Same thing here. Okay, ester, and same thing here. All right, ester. Okay. This is glycerol. This when it combines with stearic acid, it is a triglyceride, and this is glycerol or glycerol tristearate. Okay, so we're combining the name of the glycerol and the stearic acid there. And you see some of the way how we named esters, if you remember. Okay, so oftentimes you'll see when you discuss triglycerides that this is a good way to remember what they are. We see glycerol, right? Glycerol has reacted with a fatty acid, 3 of them, and we end up with esters, right? So they're esters of glycerol and fatty acids. The fatty acids in the triglyceride molecule are usually not all the same, right? In our example on the previous slide, we had all stearic acid molecules, okay? They be forewarned that in fats and oils, they're usually not all the same, okay? Natural triglycerides are often mixtures of many different triglyceride molecules. For example, okay, all right, here is a triglyceride, a natural triglyceride, and we see the glycerol portion, okay, right here, and then we see the fatty acid portion, right? So this would be from palmitic acid, this is from oleic acid combining, okay, and this last one here is from linoleic acid combining. So 3 different fatty acids combined, and this is typically what is seen. They're not usually always the same. All right, so fats versus oils. Fats, they are triglycerides that are solids at room temperature. Fats are usually derived from animals, and they're mostly saturated fatty acids. Okay, they have the high melting point, so at room temperature, right, they're going to be solids. Oils, on the other hand, are triglycerides that are liquids at room temperature. Okay, so the oils, they're usually derived from either plants or fish, and the oils are mostly unsaturated fatty acids, right? Which means lower melting point. So at room temperature, they will be liquids. Okay, so our discussion about melting points earlier goes hand in hand with the difference that we're seeing between fats and oils. All right, chemical properties of fats and oils. Hydrolysis. Hydrolysis of triglycerides. Triglycerides can be broken apart with water and an acid catalyst. Well, this sounds familiar, or it should sound familiar to you. We talked about reactions like this, right, in our chapter on esters. Esters can be broken apart into their alcohol and their carboxylic acid part, right, with water and an acid catalyst. And that reaction we called hydrolysis, okay? So we can break triglycerides apart with hydrolysis, or it can be done in the body by digestive enzymes called lipases. Let's look at a hydrolysis of a triglyceride. So here is a triglyceride. Okay, notice everything we talked about, right? 3 different fatty acid components, and here we see our glycerol side, right? So again, you can either use a digestive enzyme, or we can go into the lab and we can add water, right? And we want to hydrolyze all 3 of these ester linkages. So we're going to need 3 water molecules for every molecule of triglyceride. Okay, we have to have a catalyst. A catalyst helps the reaction along, okay, speeds it up. All right, it's not involved in the reaction, but it does speed it up. Or another way to do this is with an enzyme known as a lipase. And what happens? Okay, remember what happened when we hydrolyzed an ester. We got back our alcohol. There we got it. There's our glycerol. And the other component, right, we're going to get our fatty acids back, all of them, okay, palmitic, oleic, linoleic acid, okay? So hydrolysis, so all those reactions that we talked about earlier for the functional groups, right, we're applying them just like the hydrolysis of esters. Okay, so keep that in mind. If you don't remember that reaction, go back and review. Alrighty, saponification of triglycerides. In saponification reactions, remember what they were. All they are is a hydrolysis, but they're a hydrolysis where rather than having an acid catalyst, we use base. Okay, so in saponification reactions, what's going to happen to our triglyceride? Our triglyceride is going to be reacted with a strong base. Strong bases, sodium hydroxide, potassium hydroxide. What forms? Something different happened, if you recall. Okay, we didn't get back the carboxylic acid, we got back the salt. Okay, the carboxylate salt. And that's the same thing we're going to see here. We're going to see the carboxylate salts of the fatty acids. And when you get a carboxylate salt of a fatty acid, they are called soaps. All right. Example, let's take that same triglyceride that we had seen before. So here it is again. Okay. And same thing is going to happen. So we're going to take and we're going to see our glycerol. Here's our glycerol part. Here are our 3, right, fatty acid parts. Okay, we're going to cleave them apart with sodium hydroxide or potassium hydroxide. So let's use sodium hydroxide here. Okay, product is going to be glycerol. We get back our alcohol. That's what a hydrolysis does. And we get back the salt of the carboxylic acid. So the sodium salt, sodium palmitate. Notice the names. Remember how we named sodium salt of carboxylic acids. All right, very similar. Sodium oleate, sodium linoleate. Okay. So similar sort of naming system. Okay, so these are known as soaps. Okay, again, just like the saponification reaction that we saw with the esters, because that's what we're dealing with, an ester, right? Okay, so let's look at these soaps. Right. So we said we could use either sodium hydroxide, right, strong base, or we could use potassium hydroxide, another strong base. Sodium hydroxide, if we use that, right, that produces what is called a hard soap. And these are what we commonly find in bar soaps. If we use potassium hydroxide, that produces a soft soap, such as the ones in shaving creams and liquid soaps. Here is an example of a soap. Okay. These salts, right, of fatty acids, okay, they combine two solubility characteristics. They have a long, nonpolar, water insoluble, hydrophobic, right, hydrocarbon tail. And then over here on this end of our carboxylate salt, we have a charged, right? Look at the charge, right? Water soluble, right? Because it's a salt. Hydrophilic, water loving head, as it's called. So that's our polar part. The polar part is going to be water soluble. In water, think about what's going to happen, right? Who's water soluble? This part right here. Okay, it's going to want to be near the water. This part doesn't like water. It's a water hater. That's what water phobic means, scared of water, right? So if all of our polar parts are pointing outwards, that's going to leave all of the non-charged tails, right, the hydrophobic tails, all sort of tangled together, right? And we talked about that earlier. That gives us that entity known as a micelle. Okay, so this is what we're talking about. And this is what's responsible for the action of soaps. Okay, the micelle, right, is where the grease becomes lodged. Okay, the grease dissolves like, so it's going to stick with that long hydrocarbon tail. It's going to bind it up and we can just flush it away with water, all right, because all of these are water soluble here. Okay, alrighty, so saponification, hydrolysis, saponification. Let's move on to another chemical characteristic, right, hydrogenation. Something for you to recall again from those early chapters when we talked about all the functional groups. Remember, we said that no matter where we see the functional groups, whether they're in a small molecule or a large molecule like we're seeing now, the same reaction that we talked about before, we're going to see it regardless of what the rest of the molecule looks like. Okay, so reactions are characteristic of the functional group. So recall hydrogenation, right? In hydrogenation reactions, we studied those back with the alkenes, right? What do hydrogenation reactions do? Well, alkenes get converted to alkanes. How? Reaction with hydrogen gas, H2, and we needed a catalyst to help it along, otherwise it wouldn't go because temperatures would be too high, all right? So a catalyst, metal catalyst, platinum, nickel, right, palladium, some other metal. And this process, how is it used with our triacylglycerides? Well, this process is used to convert unsaturated vegetable oils. Remember, the vegetable oils are unsaturated, right? They're liquids, at room temperature? Well, if we hydrogenate them, we're going to get rid of the double bond, right? Or the double bonds, or some of the double bonds, and that then converts them to saturated fats. And the saturated fats, remember their physical properties, they're solids at room temperature. All right, so things like shortening, solid at room temperature. How do we make shortening? Well, we make it from vegetable oils. All right, we take them and we hydrogenate them. So we are going from unsaturated to saturated. Example, let's look at an example of hydrogenation. All right, so here we have a triacylglycerol, the same one. We're using the same one through the whole thing, okay? So if we treat it with hydrogenation conditions, okay, so 3 moles of hydrogen. So notice we have double bond, okay? And our nickel catalyst, we are going to convert double bonds, any double bonds that there are in this molecule, to alkanes, to single bonds. All right, and there we go. It happens, right? Notice we have converted, right, from an alkene to an alkane, alkene to an alkane, okay? So this is a hydrogenation. So you might have heard of things called partially hydrogenated vegetable oils. Okay, in a partially hydrogenated vegetable oil, you start with a polyunsaturated fatty acid. Okay, a polyunsaturated triglyceride, right? Okay, and partially hydrogenated vegetable oils. In those, what we've done is we have not hydrogenated everything. In this particular reaction up here, we hydrogenated everything. Okay, partially hydrogenated means not all the double bonds are going to be saturated. You're still going to have some double bonds. All right, and why do we do this? Because it allows the texture of the product to be controlled. Okay, maybe you don't want it super duper solid. Okay, maybe you want it a little bit more workable, spreadable, so to speak. Okay, so you're going to partially hydrogenate it rather than fully hydrogenate it. Okay. In the process of partial hydrogenation, what this does sometimes is it twists some of those naturally occurring cis double bonds that we talked about, and it twists them into trans isomers. Okay, and this is how we end up with those things called trans fats. All right, we move on to waxes. Waxes, what are they? They are we're still under the category of simple lipids, okay? Simple lipids. They contain a fatty acid, okay, that is joined to a long chain. By long chain, we mean between 12 and 32 carbons long alcohol. Let's see what we're talking about here. So a wax. Definitely different, right? Than a fat or an oil. Okay, a wax has a long chain fatty acid. We know what that looks like. All right. And bonded to that long chain fatty acid is a long chain alcohol. And that is what constitutes a wax. Let's look at some examples of waxes. Micelle palmitate. Micelle palmitate is an example of a wax. It's found, in fact, in beeswax. There it is. Okay. We see here what was originally, okay, a carboxylic acid, a long chain fatty acid. And over here we see a long chain alcohol. The two have combined, and what do we have? We still have an ester. It's an ester, okay? So there's the palmitic acid portion, and then over on the other side we see the alcohol, the Micelles alcohol. Let's look at another one. This is cetyl palmitate. Okay, notice the name is very similar to the way we named esters. Okay, so we talk about the alcohol portion, what's attached here, right, and then the acid portion with the ATE at the end. So this is cetyl palmitate. Okay, and again we see the carboxylic acid section, okay, right here, and then we see the alcohol part. Okay, palmitic acid portion and our acetyl alcohol portion. All right, again, when we see this, a long chain fatty acid attached to a long chain alcohol, it's a wax. Okay, wax. Think wax. They're also esters, as we said. Okay. All right, more on waxes. They are insoluble in water. All right. Think about waxes. Candle wax. Try to get that off of something with water. Not working. All right. There's no really polar portion to them whatsoever. Most of them are hydrophobic. All right. Water hating, or those big long carbon chains. So they're insoluble in water. They're not as easily hydrolyzed as fats or oils are, and they often occur in nature as protective coatings. They occur as protective coatings on feathers of birds, on fur of animals, skin, all right, leaves, and fruits. For example, sebum. Sebum is secreted by the sebaceous glands of our skin, and it contains waxes that help keep the skin soft and prevent the dehydration. We also find waxes are used commercially in cosmetics, candles, of course, ointments, and protective polishes. All right, on to phosphoglycerides or phospholipids. Phosphoglycerides. Phosphoglycerides, they are complex lipids. So we move category, right, from simple to complex, all right, that are the major components of cell membranes. Phosphoglycerides and the related compounds are also referred to as phospholipids, all right, so that's a synonym, all right, phospholipids, phosphoglycerides, same thing. What are they? Here's an example of a phosphoglyceride. Let's take a good look at it. We can pick out here, okay, anybody see here? You should all see the, well, okay, there goes my hand. The glycerol portion, okay. We see a fatty acid, right? Okay, so nothing new here, an ester linkage, fatty acid, okay. This is different, okay. We see a phosphate, okay. So phosphoglyceride contains a phosphate and an amino alcohol, okay. So this sets the phosphoglycerides or the phospholipids apart, all right. Glycerol, we see that, right? Fatty acid, and then we have a linkage to phosphoric acid, and the phosphoric acid is in turn linked to an amino alcohol, okay? Everybody should know what phosphoric acid is, all right, from our earlier chapters, okay? H3PO4, right? And an amino alcohol, you know what an amino group is, right? So it's an alcohol with an amino group on it. All right, let's look at an example. Okay, so amino alcohols, they are the most abundant phosphoglycerides. Okay, the most abundant phosphoglycerides contain the alcohols choline, ethanolamine, and serine. And these are then attached to a phosphate group in your phosphoglyceride. So this is choline. It's an alcohol, all right? Notice the alcohol, there it is. But it also has an amine group on the other end. It's a quaternary ammonium cation, okay? Where the nitrogen has picked up another bond, and so it has a plus charge. Ethanolamine, okay, is an amino alcohol. We see here, right, there's the alcohol. Okay, so let's underline the amine portion. And ethanolamine, okay. And then we have serine. Serine is an amino acid. It is also an alcoholamine. There's the alcohol part. Here's the amine part. Okay. All right. So the most abundant phosphoglycerides that you're going to find contain these various alcohols. These are the alcohol component. Okay. Let's look at some phosphoglycerides. First one is lecithin. Lecithin, these are phosphoglycerides that contain the amino alcohol choline. All right, so if the amino alcohol in the phosphoglyceride is choline, we call it a lecithin. All right, again, we're going to go back. We're going to go back and review, recall, right? Just on the previous slide, this is choline, okay? All right, 2 carbon alcohol and a quaternary ammonium, okay? So let's see if we can pick out these pieces. Remember what we said phosphoglycerides have, right? They have the glycerol. There it is, okay? Our glycerol part, okay? Always there. Fatty acid, right? Okay, fatty acid 1, fatty acid 2, okay? These are going to vary, okay? But if that third linkage has the phosphate group and, all right, that's linked to choline, here's our choline, okay? Notice, all right? Okay, notice the structure. Okay, we could see where that OH is, right? Or it was right here, CH2, CH2, and there's our quaternary ammonium. Okay, so when the amino alcohol hooked to that phosphate is choline, we have lecithin. Okay, the fatty acids at the first and the second positions here, as we said, they can vary. All right, so there would be a number of different lecithins. Okay, right? The thing that they have in common would be this last position. All right, more on our lecithins. Okay, so on the previous slide, that structure of a lecithin, right? Lecithins contain a negatively charged oxygen atoms in that phosphate group. And then they have positively charged nitrogen atoms in the quaternary ammonium salt. So that end of the molecule is going to be very water soluble, right? Charged, okay? All right, a salt, it's going to be hydrophilic, love water, right? Soluble in water. The rest of the molecule, though, is going to be hydrophobic, okay? So this allows the lecithin to act as what we call an emulsifying agent. And consequently, lecithins form an important structural component of the cell membranes. And lecithins form micelles, which play a role in the transport of lipids in the bloodstream. Commercially, however, lecithin, where do we get it from? It's extracted from soybeans, and it's used as an emulsifying agent in things like margarine, candies, ice cream, as a matter of fact, has emulsifying agents in it. Sometimes you'll see lecithin, and that provides a smooth structure. All right, our next one is cephalin. Cephalins, again, they're phosphoglycerides. These contain the amino alcohols, either ethanolamine or serine, so the other two possibilities. Recall, again, we're going to go back to where we showed all of these amino alcohols, right? So this was ethanolamine, and this one here is serine. All right, so cephalins, you're going to see either of these amino alcohols attached to that phosphate group. So here's an example. Okay, let's see if we can pick out which one we have. Let's pick out the different components, right? So here we have our glycerol component again. Okay, and here, right, we notice our fatty acid, we formed an ester linkage, fatty acid on 1 and 2, right? And then on 3, we have the phosphoric acid linkage, right? And let's see who we've got here. Let's look at it. Okay, I see serine, right? So this is a phosphoglyceride which contains serine, okay? All right, and it's known as a cephalin, okay? The serine unit is in there. It could be the ethanolamine, and it is then classified as a cephalin. All right, okay. So where do we find them? Cephalins are found in most cell membranes, and they're particularly abundant in brain tissue. We also find them in blood platelets. They, as a matter of fact, play a role in the blood clotting process. All right, we move on to the sphingolipids. Sphingolipids. Again, complex lipids. Remember our classification, right? And how do they differ from what we've been looking at? Sphingolipids contain something called sphingosine as part of the molecule. Sphingosine replaces the glycerol. Okay, so we're not going to see glycerol in sphingolipids. We're going to see a sphingosine portion. What is sphingosine? Okay, well, here it is. Okay, take a look at it. Okay, this is sphingosine, right? So an example of a sphingolipid are the sphingomyelins. In the sphingomyelins, a choline, all right, so remember what choline looks like, we saw it earlier, is attached to this sphingosine. And it's attached through a phosphate group. We also see in the sphingomyelins a single fatty acid. The single fatty acid is going to be attached right here at the nitrogen via an amide linkage. Okay, remember we talked about those. So an acid combining with an amine, right, gave us an amide. Okay, so this is what we're talking about in these sphingomyelins. Okay, we're going to have our sphingosine. This is our sphingosine right here. Okay, and we said the fatty acid is going to be attached at that amine with an amide linkage. So we'll see the fatty acid here. At the alcohol portion, we're going to have that phosphoric acid, right? And then attached to the phosphoric acid, we'll see our choline, right, which we saw earlier. Okay, so let's look at sphingomyelin. Here we have it. Okay, so you should, just like you could pick out your glycerol unit, you should be able to pick out your sphingosine unit. So here it is right here. Okay, sphingosine. Right there. Okay. And so here is our nitrogen. This was where our mean section part was. And it combined with the fatty acid. There's the fatty acid, and this is an amide linkage. Okay. And then down here where we had the alcohol, right on our sphingosine, here's our phosphate. Phosphoric acid has combined. Okay, so our phosphate. And there we see our choline. Okay, attaches to the phosphate. All right, and so this is a sphingomyelin, or which is an example of a sphingolipid. Okay, sphingomyelins, they are found in brain and nerve tissue, and in the myelin sheath. And the myelin sheath, remember, protects the nerves. Okay. Alrighty, another type of lipid, the glycolipids. All right, glyco. Where did we hear that before? Okay. Glycogens, back when we talked about carbohydrates. So is it possible, just from this name, that we're going to see fatty acids, right? And maybe carbohydrates linked together? Let's see. Okay. Glycolipids. They are sphingolipids, right, that contain carbohydrates, usually monosaccharides. Okay, so a single unit. So this is what we're talking about. So we're going to see our sphingosine. Okay, at that amine, again, we're going to see the linkage to the fatty acid and amide linkage to the fatty acid. And then down at that alcohol, right, we're going to see our carbohydrate attached. Okay, so let's look at an example. All right, this is a cerebroside. Okay, so let's see if we can pick out our portions of this. So here's our sphingosine. Okay, right here. Okay, right there. There's our sphingosine. Okay, here we see our fatty acid linked to the amine with an amide linkage. Okay, and down here to the alcohol, right, of our sphingosine, we see D-galactose, so a monosaccharide, and this is a glycolipid. All right, so they're also referred to as cerebrosides, all right, hence this name. Okay, so glycolipids referred to as cerebrosides. And the reason why they're referred to as cerebrosides is because of their abundance in the brain tissue. Okay. All right, let's move on. Let's move on to biological membranes. And we're going to begin our discussion of biological membranes looking at plasma membranes. Plasma membranes, you might remember from your biology, surround the cells. They are a lipid bilayer of phospholipids. So remember, there's two parts, right? Non-polar hydrocarbon part, right? Polar part. So the non-polar hydrocarbon tails are in the center. And the polar part of these phospholipids, right? The hydrophilic part that likes water, okay, sections, are on the outside. Some unsaturated fatty acids help give flexibility to the structure, to the plasma membrane, and helps to keep the aqueous contents of the cell inside, while also allowing certain biochemicals to pass through it. So let's look at a diagram on the next slide. A diagram of this plasma membrane. It is a lipid bilayer. Okay, so we see, remember the designation, right, that we had. We said you'd often see it rather than the whole structure for a lipid. Okay, we see the polar sections, right, the carboxyl group sections, right, pointing to the outside. All right, it's a bilayer, 2 layers. Okay, so the polar sections and the non-polar tails inside. Okay, and that constitutes a plasma membrane of the cell. All right, but this is not all. We have other structures in the membranes. We've got cholesterol. Cholesterol molecules help to add strength. Glycolipids on the surface help to communicate with other cells. Okay. So here we're seeing a lot of the names that we talked about. There are proteins that are embedded inside that bilayer that we saw on the previous slide, and these proteins are what help move certain substances, things like water, your electrolytes, right, potassium, chloride, all right, bicarbonate, right, across that cell membrane. Proteins on the surface act as receptors for hormones and other biochemicals. Okay, steroids. Steroids, I think, might be our last topic in this chapter. Steroids. What are they? Well, steroids are classified as lipids. Remember the definition of a lipid, right? Has water soluble, right? And then organic insoluble. So classified as lipids because they're soluble in non-polar solvents. But they are non-saponifiable. Remember, we had saponifiable and we had non-saponifiable lipids. So these are non-saponifiable. Why? Because the components of the steroids are not held together by ester linkages. Saponification was a reaction of esters. Okay? The basic steroid structure you need to be familiar with. You need to be able to pick it out. Okay, it contains 4 fused rings. Right, fused means they're joined together. Okay, let's look at a steroid ring system. The steroid ring systems, 4 fused rings. Who are they? We're going to see 3 cyclohexane rings. Remember what cyclohexane is? 6 carbons, right? Cyclic structure. We're going to see 3 of those, and then 1 cyclopentane, so 5 carbon ring. Okay, and they're all fused together in the following manner. This is a steroid ring system. Okay, 2 side by side, 1 a little bit skewed. Okay, and there's our 5-membered, our cyclopentane ring. So again, you should be able to pick out this steroid ring system. Okay. All right, let's look at some important steroids. Cholesterol, we said, was an important component of the cell membrane. All right, it is the most abundant steroid in the human body. Here it is. All right, we look at it and immediately it pops out. Here it is. Here's our 4 rings. All right, 3 6-membered cyclohexane, right, and 1 cyclopentane ring. That same configuration. Okay, cholesterol. All right, just point out some things to you. All right, the ending is giving us a hint. It's an alcohol. right? OL, right? And here is our alcohol functional group, okay? As well as some other alkyl chains, okay? And notice we've got an unsaturation, okay? So these things are going to change as we go from steroid to steroid, okay? But they're all going to have that ring system, that classic ring system. So cholesterol, most important steroid in the body, most abundant, I'm sorry. It is an essential component, as we said, of cell membranes. It's the precursor for other steroids, such as the bile salts, the sex hormones, vitamin D, and the adrenocorticoid hormones. And of course, medically speaking, there is apparently a correlation between high levels of cholesterol in the blood and atherosclerosis. All right, so that cholesterol that we just saw is a precursor for the bile salts. Okay, bile itself is a yellowish brown or green fluid that's produced in the liver, and it's stored in the gallbladder. Bile salts are simply the salt. All right. Their salts are going to be a carboxylate salt. So there we see the salt. All right. So let's see some of the similarities. All right. We do see alcohol, right, in this particular bile salt. This is sodium glycolate. All right. So the double bond is gone. Remember, the cholesterol was a precursor. Okay, we see some of the groups. We have 3 alcohols. We have an amide linkage, right there, and a carboxylate salt at the end. So that's why we call them bile salts. Okay, bile salts act like soaps and other emulsifiers. They contain both polar and nonpolar regions. So here's our polar region right there, right? The salt, the polar region that's going to be water soluble. And then the rest of this molecule, nonpolar as can be. And that's going to then help break fats in the foods into smaller pieces, allowing them to be more easily hydrolyzed, broken apart into their components, right? We talked about that. Okay, some more steroids, the steroid hormones. Hormones, they're chemicals that are released by the cells or glands in one part of the body that send out messages, and they in turn affect cells in another part of the body. Many of the hormones are based on steroids, and we said earlier that cholesterol serves as a precursor. Okay. The adrenocorticoid hormones, they're produced by the adrenal glands, which are located on the top of the kidney. Who are some of them? Well, we got the mineralocorticoids. They affect electrolyte balance within the body. The glucocorticoids, such as cortisol, they affect the metabolism of carbohydrates, gluco, all right? Let's look at some of these adrenocorticoid hormones. Here's our cortisol, all right? Cortisol, and again we see that steroid backbone of the 3 cyclohexane rings fused to a cyclopropane ring. Okay, and it looks like it definitely could have come from cholesterol, right, with some changes to it. So that's cortisol, an adrenal corticoid hormone. This is cortisone. Okay, notice the difference. All right, and here is where we are seeing the difference. Cortisol has an alcohol here, OL, right, was always our ending for an alcohol, right? And cortisone, right, ketone, okay, now has a ketone group right there, okay? And here we have prednisolone, all right, prednisolone. So we've seen cortisol on this slide and its derivatives. Its derivatives are cortisone and prednisolone. This is a synthetic hormone. All of these are powerful anti-inflammatory drugs. They're used to treat arthritis and asthma. And lastly, under steroids, let's take a look at the sex hormones. Sex hormones, they're produced, of course, by the testes and the ovaries. We have here testosterone and estradiol. Okay, so notice the difference. Okay, testosterone. Okay, right here, ketone. All right, estradiol. 2 alcohols. Okay, here and here. And then we have estrone. Okay. Oh, look, looks very much like estradiol, except for that alcohol is now a ketone. All right, so again, the endings are, we can make sense of them based upon what you know. All right, and then we have progesterone. Okay. So the androgens are, of course, the sex hormones that are found in the males. That's the testosterone, and the estrogens in females, the estradiol, for instance. What do these sex hormones do? Well, they regulate, of course, the production of sperm and the eggs, and they aid in the development of the secondary sex characteristics in males and females. And that, my friends, brings us to the end of that chapter on lipids. Next up, part 2, our very last chapter of week 14. See you soon.